I'm a scientist in meteorology, atmospheric science, and climate. I've worked with computer models out in the field, chased tornadoes. I've been teaching and tutoring meteorology for 25 years, and I can show you what it takes to become an expert and to gain the skills in this topic. That's today on High Peak Education.
In the table on the next page, identify storm types with all the simulations, classifying each case with the best representing ordinary O, multicell M, supercell S, convection. For this exercise, we will define ordinary cell simulations as those for which there is minimal new convective activity after initial cell, multicell simulations as those for which there is significant new convective activity after initial cell, but with no supercells present, and supercell simulations as those where there still may be much multicellular activity, but for which some of the cells are very long-lived, i.e. longer than 1 hour, and display significant updraft rotation at mid-levels, 4 kilometers AGL. Remember the defining characteristics of each of these types that distinguish it from the other two when you make the classification. So then we're going to go ahead and sort of run these simulations. So CAPE is going to be along the top, low, moderate, high moist conditions, and then high CAPE with dry conditions. Then we're also going to take a look at some hodographs here. And then so these are going to tell us like something about like the length of the hodograph, and then also what's the shape of the hodograph, and then like how many meters per second it goes up to, so stuff like that. So we're going to be comparing on the top, it's going to be a measure of instability and moisture. And then the hodographs on the left-hand side are going to be measure of helicity, which is rotation of the wind. And then the length of the hodograph is important, because the length of the hodograph is going to tell us about the amount of wind shear. So generally, the longer the hodograph, the more the wind shear. What makes storms longer lived, for the most part, is going to be greater instability and greater wind shear. Typically also greater moisture, but the moisture especially at low levels. One thing I think would be useful to do is let's summarize what some of these environments look like. Modern environmental conditions here focus on the sounding and the instability, that is the thermodynamic, and that's just going to be the CAPE and the lifting index. So that's what we mean by moderate environmental conditions. Now let's look at high instability environmental conditions. Again, focusing on the instability and the thermodynamics, but in this case, the CAPE is larger and the lifted index is more negative. That's always what it looks like for high instability environmental conditions. So the shear is what changes each row. So it's high instability, but dry conditions. So you could say dry conditions, the upper levels are lacking moisture. There is enough moisture at the low levels to initiate convection, but the parcels rise into a dry upper level environment. Okay? So something like that. So let's look at A2 and A4. So this is the low level view. I think this is like basically ordinary cells. Okay? Let's look at 4 kilometers. Okay? So this is moderate CAPE, no wind shear, and no hodograph. Let's look at this three-dimensionally. So we're going to look at the top view and then the south side view. Yeah, so you can kind of see this. What happens is there's this updraft that goes up, storms refire, but then they just go straight down. So this is definitely ordinary cells. Let's click on environment. So there's no wind to speak of. The CAPE is 2,300 joules per kilogram. -7 for the lifted index, which is not insignificant, but it's pretty small. Yeah, so we're not supposed to use the summary, but this can help to confirm. Going back to where we were, we should be able to say this is ordinary cells, short-lived, no wind shear, moderate CAPE. The summary, it says short-lived ordinary cells. They last a few hours. We have a weak cold pool, and the cold pool spreads out quickly. So I think that's simulation A2. So then we're going to go to A4. So A4 is going to be higher CAPE, but dry conditions. Let's see what happens here first. So notice I'm not seeing a whole lot happening at lower levels. Like the rain does come down, but then spreads out kind of quickly. Let's look at 4 kilometers. So this is kind of like mid-levels, especially with storms. So again, not much happening, maybe even a little bit less organized than we had before, because I think of the low amount of moisture. Let's look at a 3D view. Again, it's going to be from the top and then from the side. So what we have is this top view is, you can see things are, looks like not super well organized. And then from the side, the convective tower is not that wide. It's actually very thin. Let's look at the environment. So the cape is pretty large, 3,622 joules per kilogram, and the lifted index of -10. That's pretty significant, but there is no wind shear to speak of. So short-lived ordinary cells, absolutely. So these are going to be short-lived ordinary convection. So let's go capital O here. So that's the ordinary cells one. This, I think, is also going to be ordinary cells. Short-lived ordinary convection, strong cape, no wind shear, very short-lived, less than 3 hours, very weak, cold, narrow updrafts, limited moisture, fuel source, relatively uneventful. Let's go to B2 then. This, we have a straight hodograph that it's linear to 5 kilometers, that is. So that's like a linear increase in wind speed. The wind speed is about 10 meters per second, and it's also no curvature in the hodograph. Let's go ahead and have a look at what this looks like for low levels. All right, so we are starting to get some notion of a cold pool. So these cold pools are kind of outlined in that yellow, and you see them spreading out. And there is some cloud and precipitation there, but it's still not it's not really significant. Let's go for 4 kilometers. The cold pool there descends. We have some coherent clouds. Okay, so that's fine. Now let's go to 3-dimensional. So looking at it from the top, it looks like we have a significant enough updraft, a cold pool spreading out at first, but the cold pool spreads out somewhat quickly, and the convection reinitiates, but then it looks like the rain goes more or less straight down. Okay, so now looking at the side view, that's kind of similar story, what we see. Initial convection, cold pool spreads out, and more convection on the edge of the cold pool, but then it like kind of dies out. Again, we could always look at the environment. So 2,300 joules per kilogram of cape. One of the things that's interesting about these simulations is all the moderate simulations are going to have the same cape and the same lifted index, but the wind shears are going to be different as we go down the rows. So BRN is the so-called bulk Richardson number, and then the BRN shear is the bulk Richardson number shear.
So I wanted to interject on the video here and say a little bit about the bulk Richardson number. That's the BRN that's mentioned in this video. So the bulk Richardson number is a dimensionless comparison of thermodynamics to dynamics. In other words, buoyant effects to mechanical effects. So the idea is that there are some things that are driven by heat in the atmosphere. There are some things that are driven by motion in the atmosphere. When we compare those two things, we see something about the stability of the atmosphere, and that's essentially the Richardson number. So depending upon how familiar you are with meteorology, you know that one of the major ways we measure instability in terms of buoyancy would be the cape. And then the wind shear, that is the vertical wind shear, that is the horizontal wind, because remember, horizontal winds in the atmosphere are much, much stronger than vertical winds in the atmosphere. Remember, the atmosphere is very horizontally layered, more or less stratified for the most part. And that is the horizontal winds, how they change speed and direction with height is going to be the vertical wind shear. So that's why the most general definition of the Richardson number, if you will, in meteorology is going to be cape divided by shear. Cape is typically in units of joules per kilogram, so energy per mass. So that means we have to have shear in terms of joules per kilogram, so that's energy per mass. Cape is something like an integral of the area between the temperature profile and the trajectory of an air parcel, and it's proportional to the area on the skew T when you draw that out. Whereas with the shear, remember, shear is going to be, if you thought about kinetic energy, 1/2 mass times velocity squared. So that'd be units of joules. But if we went up per unit mass, you just divide by mass. So you just get 1/2 times essentially the velocity squared. However, in meteorology, when thinking about CAPE versus shear, we have to be careful with definitions. So CAPE is that pure instability, whereas shear is typically the mean wind vector between the surface and 500 meters. That's 1/2 kilometer above the surface. And we take that and we compare it to the 6-kilometer average wind speed. 0 to 6 kilometers is the most typical depth over the atmosphere that we calculate storm shear over. In meteorology, a lot of times we don't necessarily know CAPE and shear directly, but we often know something about the gradient vertically. In other words, how temperature is changing with height, which is related to CAPE, and how wind speed is changing with height. That's related to vertical wind shear. And it's been shown through so-called K theory that those vertical gradients are related to the fluxes of heat and momentum through thermodynamics and dynamics. So without going into a great amount of detail, we can generate the so-called gradient Richardson number. And the reason it's called gradient is because we're looking at vertical gradients of essentially temperature and wind speed. Now let's make sure you understand the terms here. So G is the acceleration due to gravity near Earth's surface. That's 9.81 meters per second squared. Theta here is the potential temperature. Subscript V means virtual, so we're including moisture effects. And then the bar here means like the background mean. When we go partial with respect to Z, that's in the vertical direction. So we're looking at how the background virtual temperature changes with height. We divide by a reference virtual temperature, so that way the Kelvin over Kelvin goes away. You get meters per second squared divided by height. It turns out that meters per second squared divided by height is going to give you something like units that should cancel with these, because here we're going to have meters per second, that's the wind speed, but then we take its vertical derivative. So we're just going to get 1 over seconds. So meters per second squared divided by height just gives 1 over second squared. But notice when we divide meters per second by meters, we just get 1 over seconds. But then we square that, we get 1 over seconds squared. So it is unitless. Remember, these Richardson numbers need to be unitless relationship quantities. In squaring them, remember, U is the zonal wind, V is the meridional wind. That is, U is in the X direction, V is in the Y direction. And typically, a lot of times we know these vertical wind shears very well, or they're relatively easy to calculate from, say, a wind profiler or a skew-T sounding, something like that. Lastly, how do we get the bulk Richardson number? Well, it turns out that a lot of times even these gradients are somewhat difficult to calculate because we don't know the values or the exact derivatives. So instead, we're going to approximate these vertical gradients in the following way. We're going to do over some interval, delta z, as opposed to a derivative. You know, algebra, notice that we're going to get g delta theta subscript v bar delta z over theta v bar times delta u bar squared plus delta v bar squared. And that's the bulk Richardson number, the BRN. So that's what I'm referring to in this video. It's essentially the ratio of CAPE to shear, but we often formulate it in terms of gradients, but those gradients are somewhat difficult to calculate. So instead, we're just going to calculate with some finite values. Bulk Richardson number, if it's very small, that means the denominator is large and shear is dominating. Not much buoyancy, so we're going to have low risk for severe thunderstorms and weak convection because we have very low buoyancy. That would be low CAPE. Notice if the bulk Richardson number is very large, that means the buoyancy dominates over the shear. We don't have very much vertical wind shear. We're more so favoring ordinary convection or maybe multicellular convection. Whereas a bulk Richardson number that's kind of in the middle, especially in the teens, that tends to favor supercells. So that's what many studies have shown over large climatological studies of these storms. So again, where the cutoff points are for the various places in terms of the types of convection, take a look at these two tables, figure out what works for this convective storm matrix. Okay, so let's get back to today's content.
Here's another thing to take a look at. Look at these flags now. You can see that they increase up to around 500 millibars, but then they stay constant above that. There is wind shear up to the mid-levels, and it's not that significant a wind shear, but then it stays the same wind all the way up. What I'm suggesting is we don't have much in the way of a significant wind shear throughout most of the troposphere to get long-lived storms. And then taking a look at the summary, All right, so we have short-lived ordinary cells. It's ordinary convection. Let's see, moderate CAPE, linear wind shear from 0 to 10 meters per second to the mid-levels, rate hodograph, some cold pull, a bit of convection reinitiation, short-lived storms, updraft, less than 2 hours. Something like that. All right, let's go to B4 now. All right, so for B4, we're going to have, back to the simulation. Let's take a look at what the storms look like at the low levels at 400 meters. All right, so we have some cold pools to note here, okay, but they do definitely spread out. Because again, as we get the updraft to go up, it kind of dries out as it goes up. All right, let's look at 4 kilometers. Each of these clock ticks, by the way, is 5 minutes. So that's like 3 hours of simulation. So not much to speak of, especially in the upper levels. In fact, I think that's worth writing down. Convection initiation at low levels, but the updraft dries out at mid-levels due to entrainment of dry air as it rises. So I think we can just tell that from the 0.4, that's 400 meters, and 4 kilometer levels. So now let's look at the 3D. The clouds as viewed from above, okay, kind of the cloud thickness, if you will. So there is a cold pool, and there is some reinitiation, but not really. This thing kind of dies out pretty quick. So you can see that convection has trouble getting itself back going. What we can say is the convection does not reinitiate much on the cold pool. There is a very weak cold pool. We do expect this is O, that is, again, ordinary convection. And then because of the lack of moisture, there is the vertical wind shear increases the entrainment compared to A4. Therefore, the ordinary cells are weak and short-lived. The recipe here is kind of important. Just because you have a lot of CAPE doesn't necessarily mean you're going to get a storm. If you have only a little bit of moisture at low levels and it's very dry at upper levels, the storm will initiate, but it'll just peter out pretty quick. The reason I mention that is the wind shear in this case actually hurts the storm development. Now, a lot of times people say, oh, wind shear always helps, always makes it better. Not necessarily. And that's because the wind shear, as the updraft is going up, we're mixing the dry air into the sides of the updraft more than we were when there was the no wind shear case, when we were comparing A4 to B4.